This lesson is going to be about representing functions as rules, tables, and graphs with two essential questions. What is a function and how can it be represented with an equation, a table of values, and a graph? That's one thing we're going to look at, specifically the graph. And how do you identify the domain and range of a relation presented as in ordered pairs, a graph, or a table? Again, we're going to concentrate on the graph part of this today. Here's an example of a rule y equals x plus 3, where x is your independent variable and y is the dependent variable. So we're going to label our axis here x, our horizontal axis, and our vertical axis here y. The rule is y equals x plus 3, and we're given several values for the domain. The domain are input values. Input values go with our independent variable, in this case x. One of the ways that we're going to end up graphing this rule y equals x plus 3, which is a function, is to create a table of values for inputs x and outputs y with a domain of 0, 1, 2, 3, 4, and 5. If we substitute 0 as a value for x into our rule, 0 plus 3 is 3, and we get an output of 3 for y. If we input 1, 1 plus 3 is 4. If we input 2, 2 plus 3 is 5. Input 3, 3 plus 3 is 6. 4 plus 3 is 7, and 5 plus 3 is 8. And we have a table of values now for input values x and output values y. Each one of these pairs of input and output values correspond to a pair of coordinates, in this case 0, 3, 1, 4, 2, 5, 3, 6, 4, 7, and 5, 8, where the first number is the x coordinate and the second number is the y coordinate, and we can plot each one of those individually on the graph here. Now, our largest y value, 8, and our largest x value, 5, needs to fit on our graph. And if we count our grid lines here, we'll be able to identify each one of these grid lines with a unit of 1, making the largest x value 8 and the largest y value 8. And so there's plenty of room if we count each box as a value of 1. So the first point, 0, 3, we're going to go 0 on the x-axis, and then 3 on the y-axis. This is going to be the first point right here, 0, 3. Moving over to the right, 1 and up 1. Here's the point 0, 4. The point 2, 5 is going to be right here, 3, 6, 4, 7, and the last point, 5, 8, is right here, barely fits on the graph. But there's a graph of the function y equals x plus 3 using a table of values, your domain, and the outputs, the y values. To finish this problem off, we've identified the domain, but we can now also identify the range, which are the collection of all of the y values, and the range for this specific set of inputs or domain is 3, 4, 5, 6, 7, and 8. All of these values right here. Here's another example. The function y equals 5x minus 6 with a given domain of 1, 3, 5, 7, and 9. Again, we're going to start out with a table of values. X's for the input and y for the output. We've got an input of 1, 3, 5, 7, and 9. With an input of 1, we're going to multiply by 5 first. Do multiplication before we do subtraction, order of operations. So 5 times 1 is 5, minus 6. Our output's going to be negative 1. Input 3, 3 times 5 is 15, minus 6 is 9. Input 5, 5 times 5 is 25, minus 6 is 19. 7 times 5 is 35, minus 6 is 29. And lastly, 9 times 5 is 45, minus 6 is 39. Now these inputs and outputs are significantly larger than the last example, so we're going to have to figure out what could we label our graph, what are the units of each tick mark on our graph, so that we can fit these large values 9 and 39 on our actual graph. There are 8 tick marks. If we make each tick mark here a value of 2, we'll have 2, 4, 6, 8, 10, 12, 14. This will go all the way up to 16. That'll fit 1 through 9. If we make each one of these tick marks worth 5, a value of 5, we'll have 5, 10, 15, 20, 25, 30, 35. This last one up at the top will be 40, and that will definitely fit our largest y value of 39. So now plotting these points will get a little bit tricky, but if we try to plot the point 1, negative 1, do that in a different color. If we do 1, negative 1, we're going to be right in here. If I can get it to draw, there we go. That's about where the point 1, negative 1 is going to be. 3, 9, we won't quite, well, 3 will be right in here in between the 2 and the 4, and the 9 will hopefully be, let's see if I can draw that, just shy of the second tick mark on the y-axis, which is a value of 10. Let's try 5, 19. 5 is going to be between 4 and 6 here on the x-axis, and 19 is just going to be shy of the 5, 10, 15, 20. Yep, right here will be this point. Try to make that a little bigger. I'll try to make that last one a little bit bigger too, if I can. Okay, 7, 29. If this was 5, 6, here's your 7 on your x-axis. 29, 5, 10, 15, 20, 25, 30. And we're going to be just shy of that. Here's 30. We're going to be just shy of that. So 7, 29 should be right around in here. Try and make that point. And then lastly, the 9, 39 here is going to be the 9 on the x-axis, and 39 will be way up here. See if I can. Yep. So there we go. We've got 1, 2, 3, 4, 5 points plotted, or things that kind of look like points plotted there on the graph representing this function. And our range, to finish this problem off, we know the domain. Our range that goes with the given domain is negative 1, 9, 19, 29, and 39. These values again right here, all the y values. Example number 3, we're going to take points already plotted on the graph that could represent a relation that's a function, and we're going to try and come up with a rule that a function rule for these points. So what we're going to do is look at each point individually and come up with a table of values, which I'll write here, table of values, and see if we can't look for a pattern to come up with a rule. So the very first point, this first one right here, has an x-coordinate of 0 and a y-coordinate of 5. The second point right here has an x-coordinate of 1 and a y-coordinate of 2. Here we have an x-coordinate of 2 and a y-coordinate of negative 1. And the last point here has an x-coordinate of 3, y-coordinate of negative 4. Now if we look for the pattern and try and establish a rule, my first guess is going to be looking at this first set of inputs, this first input and that first output. My first guess is going to be maybe we can take our x value and add 5. If we take 0 and add 5, we get 5. Let's check to see if that works here. For this example, it doesn't. If we add 5 to 1, we're going to get 6. We're not going to get 2. So we don't want to add 5. We're going to try something else. We're going to try, what if we go back here to the first example, what if we actually, let me undo that. Let's look at this input here and say, what if we take the opposite of that x value and add something to it? If we could take the opposite of 1 and add, that would make it -1, and then add 3. -1 plus 3 would be 2, so that would fit. Does that work here back at our first example? The opposite of 0 is 0, plus 3. That's not going to work because we need to add 5. So let's try one more attempt, and let me find a color here. What if we try not just the opposite, but some multiple of the opposite, so -3x plus 5. Okay, that's definitely going to work with 0, 5, because 0 plus 5 is 5. Will it work with an input of 1 and an output of 2? Plug in 1 for x here, and we get -3 plus 5 is 2. Does it work for 2 and -1? Input 2, and we get -6 plus 5 is -1. Does it work for 3 and -4? 3 times -3 is -9 plus 5. This is our rule. We figured it out. And the domain for the given graph, the domain are the x's in our table, 0, 1, 2, and 3, and the range for those domain values 5 to -1 and -4. One last example. Again, we're going to make a table of values for the given graph, inputs and outputs. The first point here, the x-coordinate is -4 and the y-coordinate is 2, -4. 2. The next point has an x-coordinate of -2 and a y-coordinate of 1. The third point here has an x-coordinate of 0 and a y-coordinate of 2. This fourth point here has an x-coordinate of 2 and a y-coordinate of 3. And this point here has an x-coordinate of 2 and a y-coordinate of -1. Now, the interesting thing here, if you remember in our discussions about relations and functions, is that for this particular graph, these 2 points have the same input, which is x equals 2, but different outputs. One has an output of y equals 3, and the other has an output of y equals -1. And the result is that this is a relation that is not a function because of the same input resulting in 2 different outputs. And one way we can quickly determine whether a graph is a function or not is to use the vertical line test, which says that a relation represented by a graph is a function provided that no vertical line passes through more than one point on the graph at a time. And so you've got 3 example graphs here. Here is an example of a graph that clearly is a function. You can see the blue points scattered about, and no vertical line in that example passes through any more than one of those points at a time. Here's a second example of a graph where the blue points are scattered so that, again, no vertical line passes through any of those points more than once. But this third example, this third graph, clearly has 3 different blue points actually all lined up vertically where a vertical line passes through, in this case, 3 points, and therefore that is a relation that is not a function because it fails the vertical line test.